Okay, so let's go with the third part of this video. I'm going to open APDL again. I closed it previously because I want to start the model again from zero. So I have already presented you the script somehow. Now I have arranged the script in a way that we see things a little bit clear. Here are the parameters that we will define in the model: the length, the height, the width, yielding, elasticity, and so on, the load, the horizontal and vertical divisions that we will have in the model, the type of element, and so on and so forth. Everything is here, but I have added some lines at the end. So here is the part in which we have defined the parameter of the analysis. So we are not extrapolating results for the view of the model. Running nonlinear geometrical, we are considering that. We are considering 100 steps, and we save all the information, and then we solve. Now, in the part of the post-processing, there might be different alternatives for getting the data. For example, displacement and reaction. But here I have some that I have found which are relatively good for following. So I'm going to explain to you the next part of the code, what is happening in these lines, but I hope they are somehow a little bit self-explanatory somehow. So here, what we have, or let me just maybe do the model again so we can just immediately see things. So I'm going just to copy these lines here from the parameter on. Or first, I'm going to copy everything. So I'm going to call this example 2, and we are just saving this in the same directory, and we change the title. So I copy everything just up to the point before running the analysis. I paste the line here, and then the model is done with the load there. So what I'm going to do here in the next lines is first we want to extract data of the reaction that we have here, and also regarding the deformation that we have in this point. Now the question would be, which is the number of the node that we have there, and which are the nodes that we have here. So for knowing that, I have this line here. So first we have a selection of the node that belongs to a line. When we define the model, we have defined 4 lines, 1, 2, 3, and 4. So in this line number 4, we have all the nodes related with the supports. So what I'm going to do is to select this line number 4. We're going to select the nodes associated to the line, and we're going to get the number of the nodes, and then we're going to run a loop for storing the number of the nodes in a vector. This vector is called node supports. So we can run this. I'm going to run the model. So the next line that I'm missing, I'm going to run the model, and then I'm going to show you what the things are doing in every step. So here you have the model is running for 100 steps with the match that I have defined. And according to the match, we reach the time point 87, which is part of the load that I have defined. It's not the total load. When we go to read the results, you can select here the last one that we have some information. So in this save 86 we have information, but when we have this number with only 9, that means that there are no results there because there was no convergence. So this is the last step, 86. We read that step, and then we can just plot the results as we did previously. Element solution, we can just plot the von Mises stress. Now you see somehow the plastic zones here are more distributed than before. So in the post-processing, we are already in post 1. When we click here in post-processing, this line happens. This one I wrote it because these are commands that happen in the post-processing. We're going to do first this thing of creating a list of the nodes that belongs to this line. So I copy that one here and I paste it. Here you are going to see the next things. We have defined some parameters. Cell node is a scalar value, and we have here a vector or an array. With this dim, we can define an array. This array has a length of the number of nodes. So the number of nodes that we would expect in this line is the number of element plus 1. So if I have defined how many elements? 20 elements, we are supposed to have 21 nodes in that line. So if we go here to the parameter, array parameters, define, we see here the array has 21 values. We can just click and edit and see which are these values. The values are 1, 52, 82, and those are supposed to be the number of the nodes that we have in this line. This will help us to extract the information later regarding the forces associated to those nodes. So this is something that you can use in any model later. Just need to know how to define things. So maybe instead of selecting a line later in a volume, you're going to select an area. So you can just select the nodes associated to certain area. So now if we, for example, go here and plot controls, put the numbering on, okay, you will see that we see the numbers only of this line because this line is selected according to the selection that we have done here. So we need to select all the model again to extract the data that correspond to all the model. So now we go to numbering again, we apply this, and now you see that we see the node of all the model. Now we want to select the node in which we will, or not select, but we want to know which is the node in which we will get the displacement, and this is going to be the node located in this position. So the node number is going to be retrieved with this function node, and we put here the coordinate x, y, and z, and then we will see which is the node associated to those coordinates. Here we paste that. If we go to the parameter scalar node tip, you see that is the node number 2. If we zoom in to that corner, here is the dynamic model mode in which you can move the model. You will see that exactly that is the node number 32 as written there. Now obviously you can just write down that directly, but if you change the match, then the node would change. That is why we have a function for evaluating which is the node associated to that position. Okay, so now we have a list of nodes that will give us information about the reaction, and one node that will give us information about the displacement. We're going to create an array for storing, for saving the forces. Now this array is going to be rewritten in each step. Why? Because since we have a list of nodes, for each node we are going to have certain reaction set, just in the other direction, but general explanation. So for each node we will have a reaction set. So we're going to have a list of reaction sets, but what we are interested is the total reaction, so the summation of all the nodes. So we're going to create first an array in which we will store the information of the reaction for all the nodes, and then later we will sum up all this information to have the total reaction result. So this array is for storing this partial information. and the array is going to have a dimension of the number of nodes related with the support, and 6 because we are going to store 6 values there. We're going to store the force in X, force in Y, the bending moment reaction, I mean the location Y and X of the node, and also the bending moment reaction. We will use certain equations for getting those things. So I just copy that, paste it here. You didn't see anything, but what happened is that we have created an array. Here is the result reaction array, which at the moment is with 0 values because we have not run anything. Now we are going to get the result for each load step. So we have run the analysis for one load step, but the load step is divided in 100 sub-steps. However, we saw that we didn't reach the 100 sub-steps. The model stopped earlier in the 86 more or less. So the first thing we need to do is to get the number of steps that the model actually ran. So this is the command for getting this number of sub-steps that we have run. So here we are going to retrieve something that is 86. So if we go here, we paste that one, then we can see that the parameter, the number of steps is the 86. This is for automatizing things. Then we can define another array in which we are going to store the results, and here we put result final, and we will have 5 values there. So it's going to be equal to 86 times 5, a matrix of 86 times 5. So I'm just going to create the vector here. And then we are going to run the next script for every load step from 1 to 86. With this line we define the sub-steps that we are analyzing. So we're going to start with 1, 2, 3 until 86. And for every sub-steps we're going to calculate the reaction forces. How do we do that? And in the vector result reaction we are going to store the reaction according to the node position I. We're going to store the number of the node. I mean, this is not actually that's something that we need. It's just from the code that I defined, and I wanted to check that everything was working. We're going to store the force X. We get the force X by this command get. That is a command that we use in the post-processing. We can get from a certain node number, we get the reaction F in X direction in Y, and the same command get, we can get the coordinate location of the coordinate X for the node number that we are analyzing. The node number is coming from the node list that we have defined previously. So we do this for every node in the support, and we will have a list of reactions. So reaction X, Y, the coordinate X and the coordinate Y, but remember that our model is defined with respect to 0, 0. If we would like to calculate the bending moment reaction here, we need to move the coordinate to the center of gravity of this line. That would be the height of the beam half. That's why I'm subtracting half of the height of the beam to the coordinate in order to have the coordinate correlated with the center of gravity. So then in the position 6, for calculating the bending moment reaction, I just have the coordinate multiplied by the corresponding force Fx, and that is going to give us the bending moment. So this is our solution for every node, but if we want to have the solution of the support, we need to sum up these values. So this is what I do in the next line. We just define m set equal to 0, and then we just sum up the values of the MZ reaction, which is the position number 6, for all the nodes in the support. So we do that, and at the end we have the reaction MZ, Vx, and Vy. So for every sub-steps, load step or sub-steps, we are going to store the corresponding reaction that we have calculated. And also, with this function get, we can obtain the displacement in the direction y and z, and we can just store that in the same matrix here. So we are going to run this command here, this loop. So you see as well at the end how the list looks like. We just run that, and then we can go here to the parameter, array, define, and here we have the result final for 86 steps for 5 columns, which are the forces that I told you. Force in X, which is something almost 0. I mean, it's not exactly 0 because of the numerical errors. Then we have the force in direction Y. We can scroll down, and you can see that in the steps 86 the force is around 25 kilonewton, something that we would expect. Then we have the bending moment, and we have the displacement Y and the displacement X. So we have all that information, and now we would like to, I don't know, copy that information in Excel, for example. So here I have other lines which will help you to copy that information into a text file. So what we do with these lines is to create a macro script, and in the macro script the next line are going to be written, in which we we open a text file, and in the text file we write the values from this array that we have defined there, and we define the corresponding format of this value. So it's a float number with 14 characters, and 11 of them are going to be the characters after the dot. Then we have something we have an space with X, and then we have the formatting for the second value, third, 4, and 5 value. So for the 5 values that we are going to extract from the table, we have the corresponding formatting, and then we just close the file that we have open, the result reaction, and that's it. And those are the lines that are going to be written in the macro. With this one we finalize the creation of the macro, and then we can just run the macro that we have created, and the results are going to store in this file, result reactions. Now, why do we put this into a macro? Because this command bwrite cannot be run immediately in this command prompt. There are some problems. That's why this is a solution that can be used for storing data in a text file. So if I copy those things and I paste them here, we can just go now to the folder, and we can see here the last modified file is this one, and here we have the corresponding results. I can open this file here, and you will see that those are the results of the table that we just saw, 25 and 1200 something. We can just copy all of this in Excel. Okay, so we can copy this file into Excel. I'm going to show you, but I know that we will have some problems, but just to show you what happens in this case. So if I copy those here, okay, so you see that everything is somehow in one in one column. We can just separate that with the corresponding data text column, and here, well, we go back. You have different alternatives. You can delimit it here with the a space, for example, and you will see that here, that at least seems to be working. But then you see that there are some problem here, that some values are moved to this line, and that is because here we have this negative sign, and therefore it recognizes that in the previous case we have a space, but in this case we don't have any space. We go to fix width, we can just see if that works, and in that case seems to be working for all the values. So we are going to copy to paste them in that way, see what happened, and you see already that seems to be working. So the first value was the force in X, force or reaction X, reaction Y, bending moment Z, and displacement Y, and displacement Z. So we can now just add a plot with the displacement, with the bending moment and the displacement Y, and see how that looks like. We add the plot. So in this case, let me just change. In the horizontal axis we have the displacement Y, and in the vertical axis we have the bending moment. And now you see something that you would expect from a nonlinear analysis, that somehow everything is linear, and at some point, due to the plastic zones, we have a decrement in the stiffness, and then we reach a certain limit, which is the plastic capacity. So that's the way you extract the data and to somehow do the model with APDL. Now what happens if, for example, we would like to change the mesh? So here, instead of using 30 and 20, we just change this to the horizontal division to 50 and the vertical to 25, for saying something. You don't need to copy the lines. What you can do is just to go back to your model. You can just clear everything. Clear, do not read file. Okay, and then here you can go to file, read input from, and you can select the text file that we have created. You click in OK, and everything will run relatively automatic. Also here you might have some problems. I have experienced some problem with this macro that I have defined, so you have to run that manually somehow. So the model is finalized, and now you see that load set not found for file x2. You just click in proceed. While processing file-based input macro or macro, an error has occurred. Should input processing be suspended? We put no, and then we will see if the macro was written or not. So in this case, the macro didn't run, or did it? I think it did run. Let me just open the macro here. Yeah, it did run, so it just worked fine. We can just copy the data once again here in Excel. We copy the data, we use text import, fix width again, finish, and then we can add a second curve here. So we add the X value, which is going to be this one, and we add the Y value, which is going to be the bending moment. Okay, now we go here, and you see that there are some differences from the first analysis and the second analysis. Now the differences are not so huge, but it is important to notice that in this case you can recognize that there are differences due to the meshing. More importantly, I have previously run this with different mesh, and now in this case with a coarser mesh you see how the result looks like, and when I have increased the mesh to the one that we see now, it looks like this. So there are differences with respect to the meshing. Now, which is the right solution? I cannot tell you that because I'm not 100% sure. It's something that should be studied because these things are always related to the type of element that we are using. So this membrane element, it has certain limitations. And you see here, at least it's possible to see, well, not now, but previously, here there is a distortion of the element. And this happens because we have a very concentrated load. So also, depending on how you define the load in your model, that might generate some problems. So it's not so easy to say which is the right solution. It requires further study. So that would be everything that I wanted to show you. Now I think you have some tools that you can use for running your analysis and study further, I don't know, matching effects, bending moment, loading effects, or boundary condition effects. Just test different things and see how everything works.